Today is polar areas, but a little bit more complicated. All right, so we are going to use the same equation for our polar area, 1/2 of the integral from a to b of r squared d theta. We're given the area of an inner loop, limosone, and the equation is 1 plus 2 sine theta. So I'm going to fill in my chart. I have 0, when theta equals 0, I have 1. When theta equals pi over 2, sine is 1, so that would be 1 plus 2 is 3. And back to sine 0, pi is 0, so again 1, and then sine 3 pi over 2 would be negative 1. So 1 minus 2 is negative 1. I'm going to draw this in. It looks like, okay, we start at 0, so this is our start. And then we swoop up to pi over 2, 3, or 3 pi over 2. And then back. So we're moving in this, oops, I graphed that wrong. Okay. So we're moving in this direction, counterclockwise direction. And what we want to find is the inner loop of the graph, the area of the inner loop of the graph. So what that is the area from just from the pole to the points on the inner loop. So just that middle part. So what I need to find is what are the values um, of the intersection at the pole. So when does the graph cross the pole, so that I know when the graph initially crosses or when the inner loop starts, then we go through the loop, and then back to the pole to complete the pole. So finding the values of the zeros tell me what the bounds are going to be for the area of my inner loop. So the zeros, I have 0 is equal to 1 plus sine 2 sine theta. Okay, so subtract 1 to give me negative 1, 2 sine theta. Is negative 1 equals 2 sine theta, divide by 2, so negative 1/2 is equal to sine theta. And then sine theta is negative 1/2 when my angle is pi over 6 past the x-axis. So when theta is 7 pi over 6, and then pi over 6 to the x-axis, so 11 pi over 6. All right, so now we need to set up our equation for our area, and that would be 1/2 times the integral from, so the inner loop starts at theta equals 7 pi over 6 and ends at 11 pi over 6. And then the equation for r is 1 plus 2 sine theta. We square that value and d theta. All right, using a calculator, I evaluated to give me 0.544, and that's rounded. Truncated, its area is equal to 0.543. All right, up next, we're going to find the area of the graph of 1 plus 2, r is equal to 1 plus 2 sine theta. So same equation. What we have is we're going to start at 0, 1. At pi over 2, the point was 3. At pi, the point is 1. At 3 pi over 2, the point is negative 1. So the loop goes like this, it passes through the pole, up to the negative radius, and then back through the pole. Okay, now the problem here is that if I get the area of the curve, I'm going to start with r is equal to 0. So from the pole to theta is equal to 0, excuse me, r is equal to 1. And then we move in the counterclockwise direction like this. And first we're going out to the further curve. So like the heart part of the inner loop curve, okay? And then what happens is once I get to the inner loop, I have the area of the inner loop that I have to add up. But right now, the inner loop is being added twice. Once from the blue area, so from basically the area from 0 onward, and then once the inner loop comes around, that area gets added twice. So to get the area, I'm just going to say the area is equal to the whole inner loop, so the whole limosome, minus the inner loop, the area of the inner loop. Okay, so the area is going to be, I'm going to take the area from, so 1/2 from 0 to 2 pi. So the whole thing, I'm going to go around the whole cycle. 1 plus 2 sine theta squared d theta minus the area of the inner loop, which we know from the problem above. The inner loop starts at, I have zeros at theta is equal to 7 pi over 6 to 11 pi over 6. So I'm going to start at 7 pi over 6 and at 11 pi over 6 to take away that double counted area. Okay, what I get is the area is equal to 8.881, and that should be truncated and rounded. Okay, find the area between the two loops of the graph of the same graph. So we're going to start at 0, 1. I said that backwards. It's r theta. So 1, 0, and then 3 pi over 2, then 1 pi, then -1, 3 pi over 2. And your curve actually starts at this point here on the positive x-axis, and it moves this direction. Okay. All right, so we're going to find the area between the loops. So what I want to do is only find the area that is from the loop to the outer curve. So this is kind of like the last one. What I'm going to do is take the area of the whole cycle, the whole area of the loop, whole cycle of the area of the whole cycle. There we go. Minus 2 of the inner loops. Because right now, if you can imagine, if I took the area of the whole inner loop, I get, what I'm doing is counting this inner loop once when I go around during 2 pi, and then I want to take it out again because it's being counted double. So I have to take out 2 areas of the inner loop from the whole cycle. Okay, so I end up with the area is equal to 1/2 times the integral from 0 to 2 pi of 1 plus sine theta squared d theta minus 2 times 1/2 of the inner loop, which is 7 pi over 6 to 11 pi over 6 of the same function, 1 plus 2 sine theta squared d theta. So the area is equal to 8.337 or 8.338. Okay, a couple more. So we're going to find the area inside of the curve r is equal to 3 sine theta, but outside the curve r is equal to 2 sine theta. 2 minus sine theta, and I see that I forgot to erase these. Okay, so I have 3, r is equal to 3 sine theta, and r is equal to 2 minus sine theta. Today, on my physical paper, I went like this, trying to zoom my physical paper. I've lost it. It's over. All right. So anyway, we have r is equal to 3 sine theta, which I know is a circle, but let's go ahead and plug in 0 in for theta. So sine 0 is 0, so we get 3 times 0, which is 0. And then sine pi over 2 is 1, so 3 times 1 is 3. Sine pi is 0, so back to 0. And then sine of 3 pi over 2 is negative 1, so I end up with negative 3. Basically, the whole cycle going through 0 to 2 pi will trace the circle twice around. So I'm going to go ahead and graph 0, 0, then 3 pi over 2. And then I know that the radius of this circle is 1.5. So I'm just going to put in some markers here to help me out. Ooh, I did not draw that very nice. Okay, we're a little elongated. All right, next. Oh, because I didn't draw 3, that's why. Okay, 1, 2, 3. Wow. And then 1.5 and 1.5. Swear, it looked a lot nicer on my paper. Okay, so that's the circle. And then r is equal to 2 minus sine theta. My a value is 2. My b value here is 1. The absolute value of my b value is 1. So 2 is greater than or equal to 2. So the limacone is convex. Okay. So I start with sine of 0 is 0. So 2 minus 0 is 2. Sine of pi over 2 is 1. So 2 minus 1 is 1. Sine of pi is 0. So 2 minus 0 is 2. And sine of 3 pi over 2 is negative 1. But with the negative, that makes it positive. So 2 plus 1 gives me 3. Okay. I will graph in 0, 2, 0. So 2, and then an angle of 0. So I'm just going to put that that's where I started, and that's where I started that curve. So pi over 2, 1, pi 2, and 3 pi over 2, 3. Kind of looks like an acorn. All right. So outside of the limacone, but inside the circle, that tells me that what I'm trying to graph is this area right here. Okay. If I imagine in my head the area inside, I'm mostly under the area of the circle and over, so under the curve for the circle and over the curve for the limacone. So I'm going to think the area, most of the area is coming from the circle, and I'm taking away. What I'm going to do is take away the area under the limacone. Okay, so basically what I need to graph, or what I need to find the area of, is the circle. Okay, so the area of the circle would be from the pole out to each one of the curves here. And I need to know how long does it take me to graph this area of a circle. Well, normally I graph from 0 to pi because that's how long it takes me to get around one rotation. But I don't need any of this area right here, right? So all I want to do is get the area. Oh, I missed a little. I don't want any of this initial area here, like right here, of the circle, okay? So what I want to do is get the area of my starting intersection to my ending intersection. So I need to find those, the starting intersection to the ending intersection. Okay, so I'm going to set the two curves equal to each other. The two curves are 3 sine theta is equal to 2 minus sine theta. Okay, so then I'm going to add sine theta to both sides. And I get 2 is equal to 4 sine theta. Divide by 4, excuse me. So the sine theta is equal to 1/2. I know sine theta is positive in the first and the second with a reference angle of pi over 6. Okay, so that means that theta is going to give me a sine ratio of 1/2 when theta is equal to pi over 6 and 5 pi over 6. All right, so the intersections happen at theta is equal to pi over 6 and 5 pi over 6. That's all we need to take that's our bound for the integral then. So the area is going to equal 1/2 times the integral of, we want to take the area of the circle, okay, minus the area of the limacone. Okay, so the area of the circle from pi over 6 to 5 pi over 6 of the circle's equation is 3 sine theta squared d theta minus the area of the limacone. So I have 1/2 times the integral from pi over 6 to 5 pi over 6 of 2 minus sine theta squared d theta. When I do this in the calculation in my calculator, I get 5.196. Okay. We look back at the equation. What I have is I'm getting the area from basically from the pole to the intersection. So like this, around the curve, okay, like this. And we're stopping at the second intersection. But then what I need to take away is I'm not actually sure I can use the eraser. So what I need to take away is all the bottom half of these radii. Okay, so that's why we need to subtract the limacone. Okay, last one. Find the area of the common interior region between r is equal to 3 cosine theta and r is equal to 1 plus cosine theta. 3 cosine theta is a circle, and 1 plus 1 cosine theta looks like a limacone with an a equals 1 and a b equals 1. So that is a cardioid. Okay. So r is equal to 3 cosine theta. For my table, I get 3, 0, negative 3, 0. And for my cardioid, I get 2, 0, nope, 2, 1, 0, 1. Okay. So for the circle, it faces the positive x-axis. So I have a radius of 1, 2, 3, and then a radius. I'm going to keep my radius of 1, 2, 3, just so I can draw in a little bit nicer circle here. okay? And then the cardioid, the long length is at 0. And, okay, so the circle also starts at this point, 3, 0. Okay, and then the cardioid starts at 2, 0. So I'll go ahead and just put a little dot. And then moves to pi over 2, comma 1, comma pi over 2. And then 0, comma pi, 3 pi over 2, 1, comma 3 pi over 2. And it's whew. Okay, so it wants the drawing these is tough for me. Okay, it wants the common area. So what we want is this area right here, okay, between the two curves, basically inside of both the cardioid and inside the circle. I notice that above, if I cut the cardioid in half or the circle in half, that the area is just that the curves are symmetrical across the axes. So I really only need to calculate the top half of the area. So what I'm going to do is look at, I notice that the curves connect right here. So I am going to figure out the intersection point. The other thing I notice is that the curve is made up of two areas, basically. One that is under the cardioid. Okay, so here's all the radii that make up the area under the cardioid. And then we have a tiny, teeny bit of area that is under the pink, the circle. Okay, so I need, and it goes like that. So what I want to do is get the area, the total area is the area under the cardioid to the intersection, okay, plus the area under the circle, okay? So we need the intersection point because we need to know when we are going to switch the bounds. I got r cosine, r is equal to 3 cosine theta, and r is equal to 1 plus cosine theta. Okay, so subtract cosine theta from both sides. So I have 2 cosine theta is equal to 1. So cosine theta is equal to 1/2. I know cosine theta is equal to 1/2 is an x-axis situation. Okay, so that means that theta would equal pi over 3 and negative pi over 3, or theta is equal to 11 pi over 3. So the two curves, the two curves intersect at theta is equal to pi over 3 and theta is equal to 11 pi over 3. But I don't really care about the second intersection because I'm going to use symmetry to help me out. Oh, I know what I forgot. After I get, since I'm only taking the area of the top part of the curve, I need to double it because we're talking about having the top part of the area be symmetrical to the bottom part. So I need to make sure I multiply this total area by 2. Okay, I'm going to set this up as the area is equal to 2 for doubling times 1/2 of the integral of, okay, this under the cardioid, the cardioid starts at theta is equal to 0, okay? And we're going to swoop and get the area till the intersection, which is pi over 3. So I'm going to get the area from 0 to pi over 3 of 1 plus the cosine of theta squared d theta. And then I need to add the area under the circle. So the area under the circle happens between pi over 3, and then the circle connects back to the pole at pi over 2. So I only need to take the area from, so 1/2, from the intersection pi over 3 to pi over 2. And the equation is 3 cosine theta squared d theta. Okay, substitute in to my calculator, I get 3.926, or the area is equal to 3.927, and it has an exact value of 5 pi over 4. Okay, these take a little bit of detective work to figure out the areas, and like what the bounds are going to be. That's probably the trickiest part, but you got this.